Okay, we've gotten to the point. We've gotten to the very last lesson of our first semester of calculus. Everything from here on out is all going to be review essentially, but this is the last lecture, if you would, of first semester of calculus. So everybody can go, that's over. No, I'm joking. Maybe you're not joking. But anyways, we have one more example that I want to go over with in regard to related rates. And this actually goes back to, for those students that were in my class as freshmen in Math 2 or in geometry, there was always a problem that I presented to you, and that was the idea of the shadow. If you are standing under a lamp, under a light in the dark at night, and you look down, you see your shadow. Well, if you walk away from that light, you see your shadow getting bigger, but you don't see a shadow behind you. There's no shadow between you and the light. There's a shadow that's formed by you from the light being blocked by you, in a sense. And so we are going to explore that idea with related rates today. Okay, so for this problem, it said a person whose height, I can't see without my glasses on, forgive me, a person whose height is 5 feet, short person here, is walking toward a street light along a straight path at a rate of 3 feet per second. If the height of the street light is 16 feet, what is the rate at which the person's shadow is shortening? And so you can see I kind of drew a little picture there. You have the street light, right? And there's a light at the top of this. And it says that this person is walking towards the street light. That's important, right? If they're walking away from the street light versus walking towards the street light, you're going to get two different things going on here, okay? Now, it gives us our rate at which they're moving. It tells us how tall the person is, and it tells us how tall, it tells us how tall the street light is, and it's asking for the rate at which the person's shadow is shortening. So here we have the street light. That street light is 16 feet tall. So I'm going to put 16 feet here. And some of you guys are going, wait, why are you putting a number in the picture? I thought you weren't supposed to plug numbers in until after you took the derivative. But remember, there's one exception. If the value is a constant, then you can plug it in. And the street light is a constant. Let's hope the street light is not growing or shrinking over time. We'd have a really warped world if the height of that light is changing over time. So the height of the street light is 16 feet. That's not changing. Then we have the ground here, and we have this person. This person is 5 feet tall. Now, granted, if they're a younger person, they're probably growing at a very small or very slow rate, low rate, I should say. But we're going to just assume that their height is a constant height. Okay. Now, if the light is here and the top of the person's head is here, then I'm going to draw the little light beam. I'll use red to represent the light beam. The last light beam that skims off or just barely is above the person's head, right? So that is the light that is shining down. So in other words, this distance from here to here is our shadow. So we're going to call this x for the shadow's length, okay? We don't know what x is. What else do we know in this problem? Well, it says that this person is walking toward the street light at a rate of 3 feet per second. This person is walking toward the street light at a rate of 3 feet per second. So she's walking towards the street light. She's going this way, or he's going this way. So I'm going to call this length here y. That length is y. Well, what do we know? What's happening here? We know that this length is what? It's decreasing as she walks along because she's walking toward the street light. So we can conclude that dy dt, the rate at which this distance is changing over time, is what? Well, it says it's 3 feet per second, but this is important. This length is decreasing. She's walking towards the street light. So we would say that this is negative 3 feet per second. Okay? So dy dt is negative 3. That's important. The question is, that's really all it gives us. It says, at what rate is the person's shadow shortening? That's the shadow. So the question is, what is dx dt? What is dx dt? Okay. Now, before we even begin the problem, what should we be able to say of dx dt? Well, if she's walking towards the light, as she gets closer to the light, we should see her shadow shortening too, because this light beam would come in here. Like if she's here, it's going to come in here, and the distance between her and the end of her shadow is going to be smaller. So that implies that the rate at which it's changing should be decreasing. Now, it may not seem like we have enough information. If I'm looking for dx dt, and I only know dy dt, and I don't know y and x, that's going to cause some confusion. But let's create an equation nonetheless and see what's happening. Well, what kind of equation do we have? We should recognize that this is similar triangles. We have one really big triangle here, and then we have the smaller triangle. I'm just going to draw it. Maybe I should draw it underneath it. The person's triangle, right? And let's plug numbers in there. That's 16 feet. This is 5 feet, so those go together. This is x feet. What is this length? A lot of people will say, oh, it's y. No, y is distance from here to the person. We're looking for the total length of the triangle. That would be y plus x. So let's go ahead and set up the equation now. It would be, 16 over, corresponds with 5, equals y plus x all over x. That looks like an x prime. I'm just going to change that to x. Okay. And these are feet. I'm going to erase them just so we don't get confused. But there is our equation. Now, you may have set it up differently. As long as things correspond correctly, you're fine. You could have started off with x. You said x over y plus 5 equals 5 over 16. You could have done a trig ratio where you said x over 5 equals y plus x over 16. Lots of different ways to do it, as long as when you go to simplify this by cross multiplying, you end up with the same thing here. So when I cross multiply, 16 times x is obviously 16x. And then 5 times y plus x, I'll go ahead and write it down, 5 times y plus x. And then we'll distribute, so we end up with 16x equals 5y plus 5x. Okay. Now I can simplify this even further before I even take the derivative. Why not simplify it? I'm going to go ahead and subtract 5x from both sides. I end up with 11x equals 5y. That's pretty clean. That's pretty nice. What do I do now? Well, I'm looking for dx dt. I have dy dt, so I need to take the derivative of this in respect to time. So when I take the derivative of this in respect to time, the derivative of 11x is going to be 11 times dx dt, and then equals, the derivative of this is going to be 5 times dy dt. Okay, that seems pretty simple. It seems pretty straightforward. And then I can just plug in values. So dy dt is -3. Plug that in here. I'm just going to put this up here. We get 11 times dx dt equals 5 times -3. So 11 dx dt equals -15. And so dx dt equals -15 over 11. Type that in my calculator just so I have a number that makes sense. We end up with dx dt equals -1.364. The units on this, because we're talking about feet here and we're talking about seconds, this is going to be feet per second. And so that's our final answer. And does it make sense? Well, yeah, because she's walking towards the street light. Her shadow length is going to be decreasing. So we see a negative rate. Now I'm going to go ahead and write the final sentence here in our interpretations because it's kind of important. We would say the person's shadow is decreasing at a rate of 1.364 feet per second. That is my final answer there. Now, you go, wait a minute, you forgot your negative. Now think about it. If something is decreasing at a negative rate, that actually means it's increasing, right? If I'm decreasing, but at a negative rate, I'm increasing. So if I'm going to use the word decreasing, that's implying the negative there. So I don't want to put another negative. The person's shadow is decreasing at a rate of 1.364 feet per second. And that, ladies and gentlemen, wraps up first semester of calculus. The only thing left to do now is to take our second quiz, prepare for our unit test, and get ready for the final. Remember, for the final, there's always 3 free response questions, and you can find the 3 free response questions along with a whole bunch of other free response questions on my playlist for the review for the final. I'm not going to tell you which 3 are the final, but they are the same types of problems, same problems, just different numbers. But I'm not going to tell you which of the 11 videos is going to be on the final. It changes every year. All right, with that said, if you have any questions, please comment below, and I will talk to you again next time.